All right, ladies and gentlemen, today, by the end of the lecture, we are going to give you the entire first law of thermodynamics for a closed system. So it's very exciting. You're looking forward to it. I know you are. You've logged in early in the morning just to get this information so you can spread it around over the weekend. So first of all, let's define what energy is, okay? And it's hard to really define what energy is. There's potential energy, kinetic energy. But it's an extensive property, right? And it includes that kinetic and potential energy of mechanics. But we want to try to figure out, is that everything? Okay, so what I like to do at this point in time, if I'm in person in the class, is I like to do something called use a fire syringe. And if you're in scouting, you might have seen something like this. So I'm going to draw this, and if you come to the in-person session on Monday, I'll bring this in here. But this fire syringe is basically, and syringe is a word that I have a tough time saying. It is it's a piston. Basically, it has a knob here, and it has a thing down here, and there's a piston here, and this piston can go up and down. And what I do, and this is a terrible drawing, look up fire syringe on YouTube right now if you want to see a better version of this, and fast forward around this. There's a piece of cotton put down there at the bottom, flammable cotton. And what happens is that if I can rapidly depress that plunger, this air is compressed so fast that what happens when you compress the air so fast, the molecules are inside of there just hanging out. This is how molecules hang out. They're hanging out like this. And then that pressure is increasing, and they start going really, really fast. And that temperature rises. The temperature is the kinetic energy of the particles. The temperature rises, and it causes that flammable cotton to burst into flames. And so we would have flames. Ooh, look at that. That's flames. Here we get it like this. We started on fire. Okay? That's a fire syringe. Now, we did not change the potential energy of the system. We did not change the potential energy of the system. We did not change the kinetic energy of the system. Okay, the kinetic, this fire syringe did not move around with some velocity. But we did change the kinetic energy of the particles inside the system. Okay, they weren't moving around, but that kinetic energy of the particles inside the system did move. So it's a different type of kinetic energy that's happening. And we're going to call that internal energy. Okay, so that's what we're going to look at here. So again, this piston didn't move, didn't change the height, no potential energy. It didn't move from side to side, locations, no kinetic energy, but the molecular energy, the molecular kinetic energy of those particles did increase, and we're going to call that internal energy. Energy internal to the system. And we have some other examples of internal energy. Okay, if I take a battery and I have my positive and negative here, and I want to charge it, hook it up, and I charge that, I know I can store energy inside of that system, of that battery. I didn't change its kinetic energy, or I didn't change the potential energy, but I changed its internal energy. I've given this example already this semester of a mixer or a paddle wheel inside a closed system. When that paddle wheel just beats that air or that liquid or whatever it is inside of there, it increases the internal energy of the system. So now we have three types of energy that we want to look at in this class so far. And I'm just going to say the change in energy. I'm just going to call it the change in energy, overall E, the change in energy. So let's go say this is the overall change in energy. Is going to be equal to the change in kinetic energy. Okay, so this is kinetic, what we talked about before, plus the change in potential energy and then we have this new energy that we want to talk about, this internal energy, and we're going to say delta here, and we're going to call that U, a capital U for internal energy. It's easy to remember U for internal energy, because there is no U in internal energy. See how that makes sense? Beautiful, wonderful. And I put a capital here. I put this as capital here to make sure we know this. Now you may notice here I have deltas. Deltas means that the internal energy is a property. I need to know what internal energy at state 2 is, internal energy at state 1 is, and subtract those two things together from each other, and I can find out what the change in internal energy is. You also might know that it says overall change in energy. I should put overall change in stored energy. That should be the word stored energy, because we store energy in kinetic energy, we store energy in potential energy, and now we're going to store it in internal energy. It's stored inside the material, increasing the temperature of the water, the excitation of those vibration of those molecules. That's what's talking about. Again, it is a property. So internal energy is saying it is a property. We do not need to know the path that we follow. We can find state 1's internal energy, state 2's internal energy. That's very, very important. You might ask, what are the units of internal energy? Well, if kinetic energy has units of kilojoules and potential energy has units of kilojoules, you're probably going to guess, hey, internal energy is going to have units of kilojoules, or BTUs if we're in our English system. Okay. Internal energy. Now, we often, in this class, don't just find internal energy, we find specific internal energy. So remember this, specific internal energy. Remember what I said earlier about when I saw the word specific, what we would do with it? Specific volume was volume over mass. Okay, so what do you think specific internal energy is? It's internal energy divided by mass, and just like specific volume was volume over mass and we labeled it as a lowercase v, internal energy over mass we're going to give it as a lowercase u. So you might see why I'm putting these bars on the top of my u's, because it's hard for me to explain to you if that's an uppercase or a lowercase u without this information here, divided by mass. So internal energy, specific internal energy, is going to have units of kilojoules per kilogram or BTUs per pound mass. This is on a mass basis. If we put this in a molar basis, U bar, these are going to have units of kilojoules per kilomole or BTU per pound mole. That's what we're going to have. So these units, this internal energy, it's going to deal with the chemical makeup of the system, chemical composition. It's very difficult to calculate internal energy. We can do it. There's models to do this, but it's very difficult to do this. And so this is the first thing that is going to say those tables in the back of the book, those appendices, that is where you're going to find how to look up the internal energy. Okay, that's what you're going to find to look up the internal energy. So we're going to have to learn how to do that. Right now, however, in Chapter 2, I'm going to give you internal energies. I'm going to say, here's what the internal energy is at state 2, and here's what it is at state 1, and we'll go from it. And then in Chapter 3, what we're going to do is teach you how to find that internal energy values in the tables of already pre-calculated stuff, so you don't have to calculate it yourself. So that's really nice. Okay, we're going to learn how to do that in Chapter 3, which is coming up, I don't know, maybe after Labor Day, I think is what we're going to do there. Okay, so let's talk about this some more. Delta U, I can write that as, that's terrible. Let's get rid of this keyboard here. Delta U, let's see if I can make a U, is equal to U2 minus U1. Or that's equal to mass 2, internal energy 2, specific internal energy 2, minus mass 1 times specific internal energy 1. But you might be saying, Dr. Wanklyn, are we talking about closed systems? And yes, we are talking about closed systems. And so you're going to say, hey, well, isn't the mass at state 2 equal to the mass at state 1? And you would be 100% correct. And that's why we're going to say mass times U2 minus U1. Okay? Because we're dealing with mass in a closed system. So now what we have so far in our equation is going to be this. The change in kinetic energy. plus the change in potential energy plus the change in internal energy is going to equal minus the summation of my work. All the different kinds of work. I could expand this side. Remember, this is all the ways we can store energy. This is all the ways we can transfer energy. Everything on the left-hand side is a property. Everything on the right-hand side is not a property. I could write it this way. 1/2 mass times velocity 2 squared minus velocity 1 squared plus mass times the gravitational pull times z2 minus z1 plus mass times u2 minus u1 is equal to minus the summation of all my work. That's where we are right now with our equation. But when we get back after the break, we're going to add one more final thing to this equation and put a bow around it and call it the first law of thermodynamics. We'll see you then.